Hello again. So in this video I wanted to connect what we know about the electronic configurations of different atoms to the nature of bonding between different elements. Chemistry is all about bonding, that is, how atoms stick to each other, and the thing is, atoms are incredibly sticky. We know this because all around us atoms stick together to make solids and liquids in our material world. Even when we look at the gas in our atmosphere, nitrogen, oxygen, carbon dioxide, water, these are all molecular materials where atoms are stuck to each other. The only exceptions to this almost universal stickiness are the group 18 elements. Discovered by Ramsay here in Glasgow, these elements are special. These atoms hold the key to understanding chemical stability, and it all comes down to their electronic configurations. So, how do atoms stick together then? In an isolated atom, the electrons are held in place by the positive charge on the nucleus. Clearly, electrons that are closer to the nucleus are held more strongly, more tightly. The outermost electrons are the least well held. When two atoms are in close proximity, the outermost electrons of one atom will begin to feel the influence of the charged particles in the other atom. In particular, outer electrons will begin to feel the pull of the neighbouring nucleus in addition to the pull of their own nucleus. So when we have a bonding interaction between atoms, it is simply that some of the outermost electrons are being shared between different atoms. When I say shared, I don't mean it in the sense of some sort of socialist utopia. We often equate that word, shared, with an equitable distribution. That may or may not be the case when we're referring to bonding electrons in chemistry. Sometimes it is equitable, often it is not. So perhaps it might be better to say the electrons are partitioned or distributed, although I like shared, as long as we don't equate it to an equal distribution. Let us start with the most unequal form of sharing, the kind of sharing where one party gets everything and the other gets nothing. I'm talking about ionic bonding. In simple ionic materials, one type of atom gives up one or more electrons to form a positively charged species. We call that a cation. The other type of atom takes one or more electrons to become a negatively charged species. We call that an anion. In the solid compound, favourable structures are formed in which attractive electrostatic interactions are maximised. That means, as far as possible, cations surround themselves with anions and anions surround themselves with cations. So let's think about that process of converting neutral atoms into ions. Clearly, you can make sodium chloride by burning sodium metal in chlorine gas. But actually that's quite a complicated process. There is breaking of chlorine-chlorine bonds, there's ripping out of a sodium atom from the metal, all of which is happening at the surface. We don't need to go there just yet. Let's imagine a simple situation where we just look at one atom in isolation at a time. The sodium atom is element number 11, and it has 11 electrons in total. The electronic configuration of sodium is the neon core of 10 electrons and one valence electron in a 3s orbital. When we ionize this atom, we're taking away one electron and leaving the 10 electrons in the stable configuration that is the neon core. Having removed one electron from the outermost orbital, the cation is now considerably smaller. That is also partly due to a reduction in the number of electron-electron interactions. So while the electron-nucleus interactions are attractive and pull the atom together, the many electron-electron interactions are repulsive and tend to push electrons apart. In sodium plus, there is one less electron, meaning 10 fewer electron-electron pairwise repulsions. Thus the atom becomes more compact. On the other side, the neutral chlorine atom has a neon core of 10 electrons and 7 valence electrons in a 3s2 3p5 configuration. When it gains an electron to become a chloride ion, the atom expands, although this electron goes into an already occupied 3p orbital. Again, this is due to the increased number of repulsive electron-electron interactions. That extra electron gives the chloride ion a very stable argon electronic configuration, but it also adds 17 new pairwise electron-electron repulsions to the system, resulting in an expansion in the size of the orbitals. Anyway, these cations and anions can arrange themselves into a stable, low-energy ionic lattice structure. So we might ask the question, which elements form cations? And for the ones that do, what charges do they have? Let's start from an observational perspective. For each element, we can look at its compounds and whether it is known to form cations and how commonly it does that. We can do that for the singly charged monocations, for the dications with a 2+ charge, and for the M3+ trications, and for the M4+ tetracations. There are some really clear patterns in behaviour here. For the 1+ cation, we see these in groups 1, group 11 and group 13. What's going on here then? For the alkali metals in group 1, we have a single valence electron in an s orbital. Remove that and we gain a stable noble gas configuration. For group 11, these have a nominal 11 valence electrons, but remove just one and we're left with 10 electrons that very nicely fill a set of 5d orbitals. Remember, a filled subshell is a bit more stable than a partly filled shell. For group 13, with 13 valence electrons, we have 2 electrons in an s orbital, 10 electrons in the set of 5d orbitals, and a single electron in a p orbital. It is these p orbitals that are highest in energy and outermost from the nucleus. Remove the electron from a p orbital and we're left with filled s orbitals and a filled d orbital. For the dication, M2+, we need to have 2 easily removable electrons. Those include the alkali earth elements, most of the transition metal series, but especially group 12. That's zinc, cadmium and mercury. Removing 2 electrons from the s orbitals leaves us a full set of d orbitals for each of these. We also see this as a stable ion for part of group 14. That corresponds to the loss of 2 electrons from the p orbitals, leaving the p orbitals empty but the s and the d orbitals full. For valent ions, well, we need at least 3 valence electrons to remove, and that's why group 3 and all of the F block, especially the lanthanides, and most of the transition metals form 3+ ions. But not, I should say, not group 12. In group 13 we can remove 3 electrons from the s and the p orbitals, leaving the d orbitals filled, and from group 15 we can remove just 3 electrons from the p subshell. All the same arguments apply for the tetracations M4+. I should point out at this stage that cations that are highly charged and very small deviate significantly from model ionic behaviour. Small, highly charged species polarise their surroundings, giving rise to a more covalent character. This is evident by the molecular nature of species like titanium tetrachloride, but by the time we get down to the larger hafnium atoms of the same group, hafnium tetrachloride is much more ionic in its character. How easily, or conversely how difficult it is to remove an electron from an atom, can be precisely quantified. We can measure the energy required to separate an electron from an atom, and this is variously known as the ionization potential energy, the ionization energy, or, because of the type of energy involved, sometimes it is known as the ionization enthalpy. These are all one and the same thing. It is simply the energy required to remove an electron from one atom. We say that the atom should be in isolation so that the energy of the system is not perturbed by a particular atomic arrangement. An isolated atom means that it is essentially well separated from other atoms, so that could be in the gas phase. And of course, since each atom is very, very small, we usually talk about the energy of a mole of atoms. That way we have a meaningful quantity of material and a meaningful value for the energy. So we can write a typical process like this. And the ionization energy, IE, has units of energy per mole of atoms. Normally the energies associated with such transformations are quite large on this scale. And so while joules per atom may be a very small number, joules per mole of atoms is better, but normally we see values quoted in kilojoules per mole or megajoules per mole. We can also quantify a second process, removing a second electron, or even the third electron, and we use a subscript in our nomenclature so that we know which process we're referring to. What I can say is that the process always requires energy. If you are physically separating opposite charges, a cation and an electron, you need to put energy in. So we would call this an endothermic process. Broadly speaking, each successive removal of an electron becomes harder because the cation charge becomes greater. In general, each successive removal of an electron costs about twice the value of the previous one. So here are some values for elements at the beginning of the periodic table. These are in megajoules per mole, but it's not the absolute value that's important here. It's the relative values that we need to look at. Let's start with lithium. So lithium has just 3 electrons. Its electronic configuration is 1s2, 2s1. So the 2 electrons in the 1s orbital are considered core electrons, and the single electron in the 2s orbital is on the outside of the atom. It is further from the nucleus and therefore less strongly bound to the atom. This is the valence electron. The table shows the successive ionization energies for a lithium atom. It costs 0.52 of our units of energy to remove the first electron, and 7.3 for the second, and 11.8 for the third. Look, it's more than 10 times more difficult to remove the second electron compared to the first. So while 0.5 is a relatively low value and easily overcome, 7.3 is huge, way too big to be overcome, and that's why there are no compounds containing the lithium 2+ ion. This much bigger ionization energy corresponds with breaking a closed shell, a noble gas electronic configuration, and it is always like that. It is always energetically too costly to remove a core electron. What about the next element, beryllium? Beryllium has just 4 electrons, 2 are core and 2 are valence electrons. It costs 0.9 units of energy to remove the first electron, and about 1.8 units to remove the second. Notice that the second electron costs about twice as much energy to remove as the first. Then the third electron, a core electron, costs an impossible 14.85 units. Too high. We will never ever see a beryllium 3+ cation in any compound. We only ever see the removal of the first 2 electrons, which cost a total of 2.7 megajoules per mole. In this period, that's it for cations. We don't see a boron 3+, boron bonds with very significant covalency. So looking across the row, from lithium to neon, we can see that the outermost electron, the first one to be ionized, becomes energetically more and more costly, as the electrons become more and more tightly held. So tightly that for boron and beyond we do not see any compounds where these elements behave as positively charged cations. Notice the discontinuity, the jump from neon to sodium. In sodium we have just 1 valence electron, just like the situation in lithium, and it is easily lost. If we plot the first ionization energy onto the main group elements, you can really see the trends. going from left to right across the period, it becomes harder to remove the first electron. Also, going down any group, as atoms become larger, the outermost electron is less tightly held, and the ionization energy decreases, meaning it becomes easier to remove that outermost electron. It's good to compare these trends in the values of the ionization energy with trends in the atomic size. Smaller atoms are more difficult to ionize. And it also makes some sense to compare this plot with which elements are metallic. And that is because the bonding in metals consists of a sharing of the outermost electrons between all the other atoms. So these electrons are not bound to any one atom, but are able to move. They are the source of our conductivity. Only elements where the outermost electrons are not bound to the atom too strongly are able to be metals. The plot is not exactly smooth. There is some texture here, and that plays out in the chemistry of these elements. But of course, it's not just the first ionization energy that is important. We may need to consider the value of the second ionization energy, or the third, or beyond. When we do that, the plots that I showed you before, of which elements form which types of cations, begin to make a lot more sense. I need to say a quick word about the electronic configurations of transition metals when they are ions, which is most of the time. Now, for the S block and the P block, there's no ambiguity in the energy of the orbitals. When we remove an electron to form a cation in the S block, we take the electrons from the valence S orbitals. In the P block, we take the electron from the valence P orbital. However, for transition metal elements, in the D block, we need to be aware of the very close proximity of the NS orbital and the N-1 D orbital in terms of energy. When we consider the electronic configuration of the neutral metal atom, we get the right electronic configuration when we fill the S orbital with 2 electrons first, and then we put the remainder into the D orbital, up to the point at which the D orbital becomes full. But for transition metal ions, it is as if the order of these 2 types of orbitals are reversed, and the D orbitals become lower in energy than the S orbital. That means to get the right electronic configuration, that is, to have the right number of electrons in the right types of orbitals, we must remove the electrons from the S orbital first before we start to remove electrons from the D orbitals. Let's look at this example with ruthenium. Ruthenium is a second row transition metal. It's in group 8, below iron and above osmium. That means it has 8 valence electrons. In fact, the electronic configuration of the neutral atom is a krypton core followed by 5s2, 4d6. Now, as a trication, ruthenium 3+ has lost 3 electrons. But for us to get the right electronic configuration for this ion, we must remove the 2 electrons from the 5s orbital first, and then remove 1 more electron from the 4d orbitals. This will leave us with a 4d5 outer electronic configuration for ruthenium 3+. Okay, that's quite a look at which elements can form cations. What about the other side to that? In an ionic compound, if one element gives up its electrons, then they've got to go somewhere. So which elements are prone to forming anions? And of those that do, what are their common charges? In terms of simple monoanionic ions, actually the number of elements that do this is very limited. A monoanion is an anion with a 1- charge. The halogen elements in group 17 dominate here. All halogens are most likely to gain 1 electron and form a halide ion. Notice that the group 17 elements are just 1 electron short of the stable noble gas electronic configuration. You know, there are a couple of other places where it's possible to form a monoanion, although this is quite uncommon. Surprisingly, although rare, gold can pick up 1 electron to form the Au-1 anion. You see from its position in the table, it is in the penultimate column of its block, just as the halogens are in the penultimate column of their block. A similar situation exists for the early group 1 elements. An example might be sodium hydride. It contains a regular sodium cation and the H- anion. Again, group 1 is actually the penultimate column of the S block. Like the process of loss of electrons, we can energetically quantify the process of gaining an electron. We call this the electron affinity, and so that we can make meaningful comparisons, and that the energies of a particular process aren't obscured by other factors like atomic arrangements, which all contribute to the energy, we define a process where all species are in isolation, or in practice, in the gas phase. The value of the first electron affinity may be either positive or negative. If it is positive, we need to add energy in. In that case, we expect the reaction to go in the opposite direction. Or it can be that the energy is negative, meaning energy is released, and the process is favourable. Let's have a look at the energies of the first electron affinities mapped onto the main group elements. There's quite a lot of texture in these values, but we can see some immediate trends. Mostly, the values increase as we descend a group, and if it is negative, it becomes more negative. It seems to be that it is less favourable to add electrons to larger atoms. That kind of makes sense. Electrons in larger orbitals feel the pull of the nucleus less than those in smaller orbitals. It also seems to decrease going across the period. This trend is more clear if we ignore group 2, group 12 and group 18. In these cases, we already have a large degree of stability due to the filled subshells. Adding the next electron here, and it has to enter an energetically higher lying orbital. So for the most exothermic reactions, the most favourable elements are the halogens. And if we think of the process in terms of the electron configuration of a neutral atom and the negative anion, we can see that the formation of a stable noble gas electronic configuration, we can see that it is the formation of a stable noble gas electronic configuration that drives the reaction. Adding in one electron, the anion becomes significantly bigger than the neutral species. So elements on the left-hand side, towards the bottom of the table, tend to form cations, and elements on the right-hand side, excluding group 18, tend to form anions. We said that taking an electron away reduces the size of an atom, and taking successive electrons away each time significantly reduces the size of the ion. Look, neutral lithium has 3 electrons. The lithium 1 plus cation has just 2 electrons, and half the radius. Okay, maybe that doesn't seem unreasonable to you. But the width, or the radius, is not the important quantity here. We should be thinking in terms of volume, the volume occupied by all the electrons. A reduction of 1/2 in length is a reduction of 1/2 cubed in terms of volume. The lithium 1 plus cation is about 1/8 the volume of the neutral atom. Here's a more extreme example. Look at cesium. Take one of its electrons away and the radius drops by 1/3. In the neutral cesium there are 55 electrons. In the cesium 1 plus cation there are 54 electrons in a much more confined space. There are some aspects of chemistry where the size of the cation is the most important feature. Going down a group increases the size of an atom, but taking away an electron reduces the size of the atom or ion. These two things combined approximately cancel each other, so there is this diagonal relationship which connects ions of similar sizes. For example, sodium 1 plus and calcium 2 plus are about the same size and show similarities in some of their chemistry. Beryllium 2 plus and aluminium 3 plus have many common characteristics. For example, both form amphoteric oxides, and this all comes back to the size of the cation. Okay, that's enough about the chemistry of ions. I want to introduce you to another very useful elemental property. It is the concept of electronegativity. It is usually given the symbol chi, That's not an X, it's a lowercase Greek letter. So the electronegativity of an atom is a measure of an atom's ability to attract electrons to itself. We quantify this ability with a number. The higher an element's value for electronegativity, the stronger the ability to attract electrons. This is going to be really useful, because given two different bonded atoms, we can compare their relative electronegativities and see which element will attract and which element will relinquish some or many electrons. The value of electronegativity is clearly related to the atom's ability to give up electrons or to gain electrons. So clearly we will relate back to the concept of ionization energy and electron affinity. But unlike ionization energy and electron affinity, electronegativity is not directly measurable. As a consequence, many people have proposed many different ways to quantify and mathematically define it. All these methods produce similar results and more or less the same rank ordering of elements. But clearly, if you want to compare values of two different elements, we must use the same type of electronegativity. We can compare a Pauling value with a Pauling value, or a Mulliken value with a Mulliken value, but never a Pauling value of one element with a Mulliken value of another element. As I say, there are many different ways to calculate electronegativity, but the Mulliken method illustrates my point. It is a balance between the energy taken in or given out when an electron is gained compared to the energy given out or taken in when an electron is lost. So let's have a look at some typical values mapped onto the periodic table. Taking any period, the value increases, with the exception of the noble gas elements, from the left to the right across the period. Looking at the groups, the electronegativity decreases going down any group. What that means for the table as a whole is that the least electronegative element is cesium, and the most electronegative element is on the opposite side, and it's fluorine. In fact, it's really useful to remember where the most and the least electronegative elements are, and it's often quite useful to know the sequence of electronegativity for the half dozen of the most electronegative elements. This will really help you when you have to describe the bonding between different elements. When we have two different elements that combine to form a compound, if we look at the difference between their electronegativities, we can make some sensible predictions about the nature of their bonding. If the difference, delta chi, is very large, then one atom strongly accepts electrons and the other atom readily gives them up. In this case, we expect simple ionic bonding and an ionic compound, where the element with the larger value of chi becomes the anion, and the element with the smaller value of chi becomes the cation. If the difference is small or zero, we expect an equal sharing of the bonding electrons and a covalent bond, where the electron density between a pair of nuclei is enhanced. By way of an example, let's have a look at a series of related compounds. If we look at the chlorides of the third row of the periodic table, that is sodium chloride, magnesium chloride, aluminium chloride, silicon tetrachloride, phosphorus pentachloride, sulfur dichloride, and elemental chlorine itself. Because elemental chlorine contains chlorine atoms bonded together. This gives us a series where the differences in the electronegativities of the two different elements gradually changes. It is greatest for sodium chloride and goes all the way down to zero for the two identical atoms in a molecule of dichlorine. For this series of compounds, the left-hand side is very clearly best described as being ionic. The materials are non-volatile, high melting, infinite lattices where we can see an alternation of cations and anions. When we melt or dissolve them, they form conducting liquids or solutions. While on the right-hand side, we see molecular species, gases, liquids and volatile solids. Structural studies show them to be discrete molecular-based structures. They are neutral, and with no separate charged parts they are not conducting. Clearly we need to use a covalent model of bonding here. We only expect to have completely equal sharing of electrons when the two bonded atoms have the same electronegativity. In other words, they are the same element. When there is a slight difference in the electronegativity, we may expect a slight distortion of the bonding electrons towards the more electronegative atom. So while very large differences give us ionic compounds and very small differences give us covalent compounds, there is an intermediate regime. There are a great many compounds that are not purely ionic and not purely covalent, but sit somewhere in between. How can that be? Or what would that look like? Well, aluminium chloride is a good example. Structurally, it looks like it's made of aluminium 3+ cations and chloride- anions. It looks like an ionic lattice, but it melts at 196 degrees C. That's very, very low for a salt. In fact, in the liquid and the vapour, we see molecules of AlCl3 and Al2Cl6. An ionic solid with molecules in the vapour? When you dissolve it in water, sure, it's a good ionic conductor. Other solvents, it can look a bit more molecular with the AlCl3 and Al2Cl6 species. This is what intermediate behaviour looks like, and it's pretty common. And we need to be aware that simple ionic models of bonding and simple covalent models of bonding may not be enough. Okay, that's all I want to say about that, so we'll end it here. Thanks for watching.